Hi, welcome to Mathematics with Tom. I am Tom, and today I'd like to continue where we left in our last matrix, in our last video, where we were looking at the basis for a space, the basis for a space. So in this, we're going to try a couple examples. So these are basis examples, and just so that basis examples. Now, when we take a look at our basis examples, let's remember that a basis is the following. It's a set of vectors that span the space and are linearly independent. Whoops. Linearly independent. So I'm going to give us a first matrix today. It's going to be, how about A? I like A as the name for a matrix. Let's try this. How about 1, 1, 1, 2, 0, 1, 2, 3, and then 1, 2, 3, 4. And what we're going to do is find a basis for the column space of A. Basis for the column space of A. Well, here's what we do. And I'll write this out. We take A and we take it to R. And once we're in R, we look at our pivot columns. The columns with pivots identify the columns in A that create the basis. It's really that clever, or that simple in a way. So here we go. Let's take A to R. I'm going to work on the A up here that I've already written. And I'm going to start by taking row 3 and subtracting row, that's an ugly looking R. Let me clean that poor R up. No R wants to look like that. Minus R1. Now notice, what did I do? That my pivot is in the top left. I already have a 0 in the second row, so I need a 0 in the third row. And with that in mind, let's do that. So then my new A becomes a 1, 1, 1, 2. 0, 1, 2, 3, 0, and then 2 minus 1 is 1, 3 minus 1 is 2, and 4 minus 1. I think I lost track what I was doing. Yeah, 4 minus 2 is, I think I made a mistake. 0. Oh, I did make a mistake. It's not what I wanted. I'm going to go here and do a quick revise. Make that a 5. 1, 2, 3, and a 5. Okay, there, that works. And then a 3. Okay. Oh, and now we can take this one more step. So let's take a row 3. And this time we're going to subtract row 2. And when our new matrix is 1, 1, 1, 2. 0, 1, 2, 3, and then we have a row of zeros, And remember that I could be writing this as the augmented matrix. Well, we don't need that. I'm going to just write it like this. Okay. And then one more thing, to get to R, we have to identify our pivot. Our next pivot is row 2, column 2, and so we need to get a 0 above and a 0 below. We have the 0 below, so the 0 above comes from taking row 1 and subtracting row 2. So let's do that. I have 1. A 1 minus 1 is a 0. 1 minus 2 is minus 1. 2 minus 3 is minus 1. And my second row is 0, 1, 2, 3, 0, 0, 0, and 0. And this is the matrix R. And now, notice a few things. I have a row of zeros. What does this tell me? This tells me that my vectors are in R3. But what this says is that the vectors do not span R3. Why? Why? Because there's a restriction. A zero row says that there's a restriction. We can't get all possible vectors. Well, what vectors can we get? And that answer is in this matrix as well. I'll show you what we can get. We take a look at our pivots. Our pivot columns tell us which columns are independent. Independent, we'll make it green for this one. Dependent columns are these other two. Those are dependent columns. So they don't add anything to our picture. All they are just linear combinations of what we already have. So I look at my columns with pivots, and I have a pivot in the first column, and I have a pivot in my second column. So we can say a basis for the column space of A is, I'm going to write it this way instead of equals. How about is the span of 1, 0, 1 and 1, 1, 2, where the span is all linear combinations. All linear combinations. Okay, that's what it means. So now note, oh, this gets even better. Why is that? Because we have two vectors for the basis of the column space. So we would say that the dimension of the column space of A, it's the number of basis vectors. That's 2. That's 2. Okay. Oh, yeah, let's go with that. Now I'd like to try another example. And this isn't to confuse you, but it's to show you that the extension of this idea of linear independence continues much further than the obvious idea of a column vector. And that is if I have the differential equation of y double prime minus y equals 0. This is a second order homogeneous linear differential equation. You should say that 5 times fast. And it has a solution. It has two solutions. In the same way that if this was y squared minus 1 equals 0, you'd expect two solutions. Well, two derivatives does the same. But each solution is a function. One of your solutions is y1 equals e raised to the x. And your second solution is y2 equals e to the minus x. So, in other words, these two are clearly independent. Like, for example, if I take c1 and I multiply it by e to the x, and I take c2 and I multiply it by e to the minus x, well, e to the x and e to the minus x, they are not like terms, meaning they cannot be combined, meaning the only way to combine them is if there's 0. So in other words, c1 has to equal c2 has to equal 0. So y1 and y2 are linear, are a basis. Goodness, all I have to say is a basis. It gets, that just adds our dimension of discussion, because once those two functions are a basis, then then the span of that basis is all possible linear combinations. And so we say that the general solution, or the homogeneous solution, is all linear combinations of the basis. Y1 plus C2, C2, Y2. And again, this is just like the C's, just like you expect. C1, C2, all they are is just scalars, but in differential equations, sometimes you see them with capitals. So you can say that the solution to the homogeneous equation, the one that equals 0, is very simply the linear combinations of C1, e to the minus, be consistent, e to the x plus C2, e to the minus x. That is the span of the solutions for that differential equation. All right, one more. Oh, so the dimension of the solution is 2. 2 independent solutions. Okay, one more I think is in good order. One more. Let's do this. How about M? M is the set of 2 by 2 matrices. Find its basis. Oops, I'm going to bring down my line here, kind of coming to the edge of my screen. So find the basis, or a basis, but I'm going to call it, well, you know what, I should be more correct. Let's be precise. Find a basis. All right, well, let's take this apart. M, normally we write it as the matrix of A, B, C, D. So what I want is a linear combination that's the most basic linear combination from which I can write any possible M. Upper triangular, lower triangular, diagonal, symmetric, all of those. Even the 0 matrix has to be obtainable. Well, what if I do this? What if I think of this as, I have an idea. Let's break it out by its components. How about A, 0, 0, 0, plus 0, B, 0, 0, plus, I'm going to bring it down here plus 0, 0, C, 0, plus, the last one will be 0, 0, 0, D. Whoa, look at that. Well, right now we just have it as the sum, but we can make it a linear combination as this is just A times the matrix of 1, 0, 0, 0, plus B times 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. Oh my gosh, and there it is. But it gets, look at how clever this is. And you might say, I don't see it. And that's okay. It takes a little bit. Notice this. Are these linearly independent? Well, if I removed the A, the B, the C, and the D, I would get the matrix of all ones. And notice, if I just look at, say, maybe these two, the first two matrices right here. Well, because B has a 0 in this first element, I can't add anything from this element to anything in the same position on the first matrix, the first basis vector. That matrix is a vector. The only way I can get those two components to add to 0 is if that first one is a 0. Well, how in the world would I do that? Well, to get to 0, to show that this is a linear independent, then what has to happen is A has to be 0. Whoops. A has to be 0, but B has to be 0 so that I can add that to C. Oops. Sorry. B, but that has to be 0, but so does C, so does D. And if all of those equal 0, which we just said they did, then which they do, that's the only way to get 0. In other words, the matrices, we'll call them A1, which is 1, 0, 0, 1. A2, 0, 1, 0, 0. I'm going to move this up a little bit. A3, 0, 0, 1, 0. Finally, and A4, 0, 0, 0, 1 form a basis for M of dimension. How many components are there? Or how many vectors? How many vectors in our basis? 4 of dimension. Let me write that way. Dimension of M equals 4. And I'm just going to write that. I've said it, I think, but just to be clear, in this case, what makes this so unique is both of these problems, look at them. Both of these problems were so special because look at this. The vectors can be more than a column. What more? They can be, oops, I'm going to erase that column word. That doesn't look so good. What else can they be? More than a column. On our first example, we have functions. And in our second example, we have matrices. You could even have a polynomial, but we're going to stop with these two because those are some pretty elegant solutions of basis vectors, and of the dimension of that basis. I hope that helps, and thanks for watching.